Okay, thank you for the introduction. In this lecture, I will talk about the basics of graph neural networks. And first, I will talk about the definition of graphs, and we will see that many data, including chemical graphs and social networks and many other graphs can be represented as a graph structure. And we will see that graphs are everywhere. And it may be more general than you might expect. And many data, including images and text and knowledge graphs, and the combination of them, multimodal data, can be represented as graphs. And that's the strengths of graphs and graph neural networks, and why we should study and use graph neural networks. Okay. First, I will define what graph is. Graph is a data structure representing relations. And there are two components in graphs. The first one is node, which is an atomic element of the graph. And the second component is edge, which connects two nodes and represent relations. This figure shows an example of a graph which have 7 nodes and 8 edges. As this figure shows, an edge connects exactly 2 nodes and shows relations between nodes. And this is an illustration or visualization of a graph. And mathematically, a graph is defined as a pair of the set of nodes and the set of edges. And this is an abstract definition of a graph. And to make it concrete, we need to specify what node means and what edge means. For example, if we said the node is a person and edge is a friend relationship, then the graph is a social network, which shows the social relationships between people. This figure shows the social network of 7 people. And this figure shows this person and this person are friends, and this woman and this man are friends, and so on. And this is a very small example, and we can imagine much larger social networks with billions of people or millions of people. For example, 3 billion people in the world have accounts on Facebook, so we can build a social network, very huge social network where billions of people participate by exploring the Facebook data set or the Facebook platform. And by analyzing such huge social network, we can draw many facts and patterns and conclusions from it. And such social networks are the basics of many domains like social science and advertisement and marketing and recommender systems. And we will see how we can use such social networks to solve real-world problems later in this lecture. And the next example is transportation network, where a node is a city and an edge is a load. And this figure shows a connection between 7 cities. And we can also imagine another kind of transportation network where a node is a station and the edge is a railway, and so on. Or we can construct a transportation network by combining such networks where a node is cities and stations and shows the geographical connections between cities and stations and so on. And a chemical compound can also be represented by graph, where a node is an atom and the edge is chemical bond. Typically, a chemical compound has some attributes. For example, a node typically has an attribute vector which represents chemical atomic type, like hydrogen and oxygen, nitrogen, and so on. An edge also has some properties like single bond, double bond, a triple bond, and so on. And this is a very small example, and maybe not doesn't make sense, but we can imagine larger, more complex real-world examples like DNA and proteins can also be represented by graph. And such graph representation and graph neural networks are the basics in many domains like chemistry, life science, and material science, and so on. And we will see how we can use graph neural networks to aid drug design and chemistry later in this lecture. And graphs are very flexible and can represent many kinds of facts and relationships. A knowledge graph is an example where a node is an entity and edge shows relations of the facts. This small example shows knowledge graph about many entities around Florence city in Italy. Even this small example shows tells us many facts about these entities. Like we can know that Verrocchio was born in Florence, who was an artist and who was a teacher of Leonardo da Vinci, who was also an artist. And he drew this picture, and this picture was can be seen in the museum in Florence and so on. And we can also think of many kinds of facts represented by knowledge graph, and the scope of knowledge graph is not limited. And we can think of, for example, the knowledge graph about you and me. And for example, we can construct a knowledge graph about me. Like Ryoma Sato is a researcher, and he is interested in graph neural networks, and he was born in Osaka, Japan, and he participated in machine learning seminar and so on. And such facts can be summarized as a knowledge graph. And we can also construct very huge knowledge graph from data gathered from the internet. And actually, there are very huge knowledge graph is available on the internet, like with billions of nodes and facts and relationships. And we can analyze such kind of huge knowledge graphs and extract many facts and patterns, and can utilize them for many downstream tasks like text analysis and image analysis and question answering and so on. And we will see how we can use such knowledge graph to boost the performance of downstream tasks later in this lecture. Okay, and actually an image is also an example of a graph. Image is a special case of a graph, which has very special pattern and regular grid-like pattern, where a node is a pixel and an edge is a spatial adjacency. And the typical image graph contains many nodes. For example, if an image is 1,000 pixel by 1,000 pixel, then it means this graph contains 1,000,000 nodes. So graph is more general than an image. And also a text is a special case of a graph, where a node is a word occurrence and edge is adjacency. The text is a very special case, which shows regular linear shape patterns. So conversely, we can say that the graph is more general than a text and can represent many forms of data and patterns, because not only the linear patterns, but also a graph can represent many complex relations, like graphs can branch and merge and can represent many kinds of data. And also, we can think of the combination of many graphs, right? Combination of text graph and knowledge graph. In this example, we combine text. Bob visited Florence and enjoyed work by Leonardo da Vinci. And we attached a knowledge graph to it by connecting the word occurrence Florence to the Florence node in the knowledge graph. And we connect the Leonardo da Vinci node to the node in the knowledge graph. And by analyzing this combination of the graph, we can draw many facts and relationships from the knowledge graph. For example, from this knowledge graph, we can know that this picture was drawn by Leonardo da Vinci, and this picture is in Florence. So we can conclude that Bob might have seen this picture in Florence. Or we might conclude that perhaps we can conclude that Bob might visited the Verrocchio's house in Florence, or we can extract many information from the knowledge graph part. And these information are not shown in the text explicitly, and these knowledge and information, like this picture was written by or drawn by Leonardo da Vinci, is an implicit context of the text. And it is difficult to draw such information solely from the text data, but we can utilize such kind of auxiliary data or auxiliary information just by using knowledge graph. And by doing such kind of inference, we can boost the performance of many kinds of downstream tasks, like question answering based on the facts or the named entity recognition or post-tagging and so on. And we can also consider more complex kind of data, like by constructing graph by combining the entire corpus with millions of documents. And we can also attach a huge knowledge graph to the corpus and can analyze such huge graph to extract medical patterns and information. So that's the strength of graph. We can unify such very complex and messy data into a very elegant way. So this is a recap of the first part. The first message is the graph is very general and flexible, and it can represent many kinds of data, many forms of data, including social relationships, chemical compounds, and images and texts, and many knowledges, and the combination of them, and so on. So thanks to such flexibility, we can process many kinds of data under the same way using graphs. And so once you learn how to handle these graphs, you can process many forms of data in the unified way, including text, images, and the combination of them, and the multimodal data, and so on. So that's why we want to learn how we can process graphs and graph neural networks. Okay, so next I will talk about the graph tasks, what we are aiming at to solve in this lecture. Roughly speaking, there are 3 types of graph tasks: node level tasks, like node classification, regression, clustering, in which the unit is a node. So for example, if we have a graph with 10 nodes, then we will make 10 predictions, and the number of samples is 10. So this is a fine-grained problem. And by contrast, a graph level task like graph classification and regression generation aims at graph level prediction. For example, we level the entire graph. So we handle each graph. And in edge level tasks like link prediction and classification, we handle each edge as a unit. For example, in link prediction, we predict whether there is an edge between a pair of nodes. And more precisely, we will see an example of node classification. Suppose we want to estimate whether each person are interested in soccer or not in a social network. We're given training examples which show which person likes or interested in soccer or not. And we are given a social network, and we know that she is not interested in soccer and he likes soccer, and so on. And we want to estimate the levels of remaining nodes. And first, we consider typical classical methods like neural networks, like multi-layer perceptron and SVM and land forest. And such methods handle each individual separately. The typical procedure would first construct a feature vector like he's in his 20s and he's male and he lives in Osaka and so on. And we first make a training data set with this kind of type, like the pair of such feature vectors and level, like positive or negative. And by using these data, we train a model, and in the test phase, we feed this feature vector to the model and predict the level of each person. This is a typical procedure of the machine learning for vector data. And by contrast, graph-based methods use both information from the graph and feature vectors. Not only feature vectors, we also use the signal from the graph. So we can expect that we can achieve higher performance than the methods just using vector data. This is a typical situation where we want to estimate the level of her interest, her preference. And the feature vector says that she is in her 40s and she's female, she lives in Tokyo, and we might conclude that she doesn't like or she is not interested in soccer based on this feature vector. But by observing the graph information, we can know that all of her friends are interested in soccer. So by combining these information, we can conclude that she is interested in soccer because she has many friends who like soccer. So compared to using just feature vectors, we can use much more richer data and can conclude more robust and more accurate predictions. This is a node classification example. And for those who are familiar with computer vision, it may be easier to understand the node level problems as an analogy to the dense prediction. As I said before, an image is an example of node of a graph where a node is a pixel. So node level prediction means pixel level prediction. So it means dense prediction, like segmentation. Given image, we want to estimate each levels of each node. So this image segmentation is an example of node level classification. And by contrast, the node level classification is very finer level classification compared to graph classification. By contrast, graph is more coarse level prediction. We want to estimate the level of each node. Like in this example, we want to predict the efficacy of chemical compounds. For example, we know that the top compound is efficacy, drug effectivity, and the second one is positive, and the third one is negative. And we want to estimate the level of the last example. This is an example of graph classification. So as in the previous example, we can say that graph problems correspond to image problems like image classification. We classify the entire image into one category. And you may think that the graph level problems are more natural than node level problems, but actually, as we will see later, graph neural networks can handle more naturally the node level problems than graph level problems. So we will, for the moment, focus on how we can solve node level problems in the following slides. And later, we will come back to the graph level problems. Actually, we can solve these problems in a unified way using graph networks, but node level problems are more natural in the graph formulation. And we need one more mechanism to handle graph level problems. And finally, we will see an example of edge level prediction. Like the typical example is link prediction, which predicts existence of edges. For example, we are given a social network in Facebook like this, and we want to predict whether these people are friends or not. And the social network defined by Facebook may not be complete. For example, these two men are not friends on Facebook, but they may be actually friends in the real world. There may be some missing links in the social network defined by Facebook. So we want to find such relations based on the incomplete social network defined by Facebook and find such peers and want to recommend such peers to these people, and so that they can find each other on Facebook easily. So user recommendation can be formulated as link prediction. And standard recommender systems like item recommendation can also be formulated as link prediction, where we have a graph with users and movies and nodes, and consumption or buying history information are encoded as links. And we want to estimate the existence of edges in this graph. And by doing so, we want to know that who wants to watch, or if there's a missing link between the users and movies, and by showing such movies to the user, we can help users to find movies that he would be interested in if he watched them. So far we have seen many examples that can be formulated as graph problems, like user classification, segmentation, image classification, recommender systems, and we can also define text-like problem like post tagging, and text classification can also be formulated as graph problems. So such flexibility and generality is very important point to consider graph neural networks and graph-related problems. And the important point is that graph neural networks can solve all of these problems in a unified way. GNNs can solve image classification, image segmentation, and recommender systems in a unified way. So we may say that graph networks all you need when you learn machine learning. And also, maybe graph neural networks are more general than you may expect. For example, multi-layer perceptron have universal approximation power, as Masaki told in his lecture, but actually GNNs are more general in some sense, as we will see later in this lecture. And also, you may think that transformers are very powerful machine learning models because it can solve many natural language processing tasks, and also it can solve image classification by vision transformer. But actually, as we will see later, transformers are a special case of graph networks, and graph networks are more general, or at least as general as transformers. So the conclusion is graphs and graph networks are very general representation and methods. So that's why we want to know or learn and use such representation methods. Okay, so we are well motivated to learn graph networks, so we will proceed to learn how we can solve these tasks using graph neural networks. GNNs, graph neural networks, or neural networks for graph data. They are basically take graph data as input and output the graph. And do not be confused with graph-shaped neural networks like MLP. MLP, or multi-layer perceptron, looks like a graph, just as shown in the bottom left. Yeah, so GNNs are neural networks for graph data, and it's not graph-shaped neural networks. It's different from graph-shaped neural networks. MLP, multi-layer perceptron, looks like a graph, as bottom right figure shows. There are neurons, and neurons are connected by edges, and this is a graph. But MLP is not graph networks because MLP handles vector data. So we can say MLP is vector neural networks, not graph networks. And GNNs, indeed GNNs also look like graph, but that's not why they are called graph networks. But because they handle graph networks as input data and output data. And this is a problem setting of graph networks. We are given a graph with node features, G. This is a problem setting of graph networks. We are given a graph with node features, G, V, E, X, and V is a set of nodes, and E is a set of edges. And they define the graph, and the characteristic of the problem setting is that we are given node features. For each feature, for each node, we are given a feature vector. And these features are aligned for all nodes. It means that the number of dimensions are same for all nodes, and each dimension means this indicate the same meaning for all nodes. And given G, we want to output graph-aware node embeddings, ZV. And this embedding contains much information about the graph structure, and this is a goal. And once we obtain ZV, we can classify nodes by applying MLP or any kind of prediction heads for each ZV independently. That's because ZV already contains much information about the graph structure. So even if the application is independent, we can draw the information from the graph structure and can carry out the graph-aware prediction, because ZV is already graph-aware. So for the moment, the goal is we want to output the graph-aware node embeddings. Okay, and let's see how GNNs solve this problem. The idea is very simple. GNNs has two phases. First, GNNs initialize a node state by node features, like this. HV0 is initialized by XV, which is a low node feature in the input. And in the second phase, it updates states by aggregating information from the neighboring nodes by this. HVL plus 1 is a hidden state. of node V in the L+1 layer, and we compute this by using the FAGL theta, which is called aggregation function. It takes two inputs. The first one is HVL, which is a previous state of the node V. And the characteristic of graph networks is the second argument, which is a set of the states of the surrounding nodes or neighboring nodes. The neighboring nodes means the nodes that share edges with node V. And this mechanism, or the second part, the second argument is called message passing, or the message means the HUL, which is the previous state of the surrounding nodes, and node V receives such messages from the surrounding node and compute the next state of the center node. And let's see how GNNs work by illustration. We have the graph with 7 nodes, and recall that GNNs first initialize the node state by the given low node features xv. Xv can be, for example, in social network case, user profile vector, or in the chemical compound, xv can be the indication function or one hot vector of the atomic type, and so on. So this is the initial state. And in the message passing phase, the GNNs aggregate the features or the hidden state from the neighboring nodes. For example, let's focus on the node 5 in the light. It gathers information from the surrounding node 4, 6, and 7. And let's consider very simple aggregation function, sum aggregation. Then the hidden state of the node 5 is x4 plus x5 plus x6 plus x7. And we also apply some transformation to the results of aggregation, like linear transformation by W, and apply nonlinearity to it, and get the next state of it. And the important point of graph networks is that the aggregation function is shared for all nodes. So the arguments are different from nodes to nodes, but the transformation function defined by matrix W and the nonlinearity or activation function are the same or shared for all nodes. That's basically because we want to generalize to unseen nodes, and we do not want to blow up the number of parameters in GNNs, and also we want to align the space of hidden features for all nodes. So basically the same procedure are done in all nodes parallelly and update the states of all nodes. And this process is stacked just like multi-layer neural networks. And in the next layer, we are given a hidden state from the previous layer, and we gather the information of the previous state, the states in the last layer in the same way. And the transformation metrics can be different layer to layer. It can also be shared, and it depends on the cases or the tasks which we should apply, which should be adapted. But basically, the basic choice is to use different parameters for each layer. And this process is repeated. And finally, we obtain the node embeddings, ZV. This embedding contains many information about the surrounding nodes and the graph structure around the center node. And we apply the predictor to this embedding independently. And we can predict the level for each node. And in training, we can adapt any kinds of laws you want, like the cross-entropy laws in classification and squared laws in regression and whatever you want. And we can compute the loss function, and the message passing mechanism can be differentiable. So we can train the model and all parameters by backpropagation as usual. So yeah, very simple. And Also, it should be noted that GNLs are sometimes called graph convolution. This can be intuitively understood by analogy to channels. Convolution neural networks gather information from the surrounding pixels, and the receptive field is typically rectangular, 3 by 3 or 5 by 5. And this is because an image is very regular grid shape graph. And by contrast, the graphs have very irregular shape, and we cannot predefine the receptive field. So we GNLs adaptively define the receptive field based on the graph structure for each node, and gather the information from the surrounding nodes and pass the results to the next layer. So they're a complete analogy to the image convolution and graph convolution. And actually, there's a slight difference between the image convolution and graph convolution, because image convolution basically takes the direction into constellation. It applies different filters to the upper left corner and right left corner and right corner and so on. But graph neural networks apply the same transformation metrics to all the surrounding nodes. It applies in a symmetric way. So this is a difference, but we can also define the graph networks can use the edge information like relational graph convolution or so on to recover the definition of image convolution. And this is very intuitive explanation, and actually there are deeper theory why we can say graph neural networks can be defined as convolution in terms of signal processing terms. And this is beyond the scope of this lecture. So for those who are interested, please refer to the literature in graph signal processing and graph layer analysis in the literature. This survey paper is very easy to understand, and I recommend this paper if you're interested in. Yeah, actually we can define the Fourier analysis of the graph signal, and by using this terminology, we can define the convolution of GNLs in a similar way as a convolution or Fourier analysis of the regular Euclidean signals. Yeah, but it's the scope, beyond the scope of this lecture. So yeah, please refer to it later. So this is the definition of graph networks, and the important property of graph neural networks is that the aggregation function can be any function, and generators are more general than standard neural networks. And let G be any neural network you want to use, L layered neural network by G1, G2 to GL, and GL defines the Lth layer of the neural network. And GL can be any layer like self-attention, MLP convolution, or batch normalization, or any layer you want to use. And let GNL be, let's define the GNL as follows. F shader arg L is defined as ignoring the second argument, just apply the GL to the first argument. And it is clear that it's easy to prove that this GNL defined by this equation can output exactly the same as the neural network at hand G. So this is a special case of GNL that ignores all the neighboring nodes or the second argument. So this is very limited and abbreviated graph neural networks. And even so, we can reproduce any neural networks. And we can expect that by incorporating information from the neighboring nodes or the second argument, we can use more information and can improve the performance more than the standard neural networks. And this generality provides many implications in practice. The first, we can use this fact to define or design graph neural networks. If you already have a graph neural networks for the task at hand, you can design GNLs based on it by adding message passing to it. You can first use such good neural networks as GL, and you can add some this component, or this is the previous slide. You can first you can start from the simple GL function, and you can, for example, concatenate the information from the surrounding node and pass it to the next layer and so on. And we can expect that such graph networks also work well as initial good neural networks. And for example, if the node features are images, then we can start from the convolutional networks or vision transformer at GL, and then we can add message passing mechanism to such neural networks and enhance the performance by utilizing message passing mechanism. And also this fact can be used to debug graph networks. For example, if you are in trouble with GNNs, you can remove all the edges and fall back to standard neural networks. Then if you still have some troubles, then it means that there are some bugs in the more basic part of the neural networks. It is not due to the graph part. And if you do not have any troubles with such abraded GNNs, then you may find some bugs in message passing part. So this can help debug GNNs. And also we can use this fact to define good graph structure. And like I told before, you can start from no edges. This corresponds to standard neural networks. And suppose we have some relations and we can use any kind of edges from it. And we are wondering which types of edges we should use in this task. Then you can try adding some edges to the standard neural networks and measure the performance of such GNNs. And if the performance is better than the standard neural networks, then we can adapt it. And if we can observe drops in accuracy, then we give up using such relations and proceed to next relations and try different kind of relations. And by doing this procedure, we can ensure that GNNs are not worse than standard neural networks. We can start the performance of standard networks, and we can improve the performance by adding good edges. Okay, so this is how we can use graphs to boost the performance of neural networks. And let's see some examples from the basic data set, caller data set, which is citation network, where a node is a paper, and node features contain Bugaboore's vector of the abstract, and edge UV indicates paper U cited U paper V. And the target level, node level, is category of the paper. This is basically a text classification task. We are given a paper, we want to estimate the category of that paper. But the difference from the standard text classification is that we are given citation information as well. And in this example, we consider simple one-layer neural network or linear neural network and linear GNN to make the difference clear. And let X be the allow node feature, Bugaboore's vector of the abstract. And let HV be the linear transformation of XV. This corresponds to standard linear layer or linear model. And let ZV be like this. This is an aggregation from the surrounding nodes, surrounding HUs. And this is basically, this is basically an average of neighboring H's. But this is very a bit tricky normalization factor. It should be NV plus 1 in the standard average, but we adopt square root of NV plus 1 times NU plus 1. And yeah, the reason why we adopted this kind of normalization is very difficult to explain, but intuitively, we can explain that we use this normalization because we want to make the inference from U to V and V to U symmetry. And by writing down this aggregation by matrix form, the matrix would be symmetric. And the more detailed explanation is that actually we can prove that the spectra or the eigenvalues of this aggregation can be bounded by 1. So we can prove that we do not blow up the norms of H or the embeddings by this aggregation. But yeah, this is, I'm not sure this can, this makes sense, but yeah, if you're interested in, you can use, or you can refer to the literature in graph signal processing and graph spectra analysis. I referred to in the previous slides. The survey paper of graph signal analysis provide more detailed reasons why we use these types of normalization. But anyway, it is not, you do not need to understand the reason for the moment, but yeah, please understand this by the simple average of the neighboring HUs. And this form of aggregation is called GCN layer or graph convolutional neural network layer. And yeah, we can define, we defined the graph or node embedding ZV. After that, we predict the node level by softmax of ZV. And we trained this network by standard procedure. And this is a result for this example. And the left panel shows the visualization of low features. We applied t-SNE to the low feature XV. And this shows that the embeddings are very noisy and messy, and it doesn't care graphs much, or does not care graphs at all. And in the middle panel, we showed the t-SNE to the HV. This is the embedding of the standard neural network or linear neural network. And yeah, this is clearer than the previous example, but the cluster is not concentrated, and it doesn't care the graph at all. So there are messy links between clusters. And the light panel shows the general counterpart, which is the t-SNE to ZV. And this figure shows clearer clusters, and we can see that the edges are very concentrated, and these embeddings care the citation clusters so that the edges are not do not cross their clusters. So we can see that representations are improved by the aggregation or the message passing mechanism. And be aware that the aggregation function do not have any parameters. So the number of parameters are exactly the same for the standard neural network and GNN. Like this is a previous slide. The aggregation, taking the average of HUs do not have any parameters. So this is very simple transformation with no parameters. Nevertheless, such aggregation improve the quality of representation much. And this is the power of message passing and graph neural networks. Okay. And the question is why such simple aggregation can improve the embeddings. The simple answer is that nodes with the same level tend to be connected. For example, in the citation network case, theory papers tend to cite theory papers, and DeepNet paper tend to cite DeepNet paper. So the papers with the same level tend to be concentrated in the citation network. And this tendency is called homophily. The prefix homo means same and identical, and the prefix phily means liking for and tendency towards. So homophily means tendency linking towards the same level. And thanks to homophily, the signal of the same level is reinforced by aggregation or taking the average of some surrounding node. And this can also be understood by the law of large numbers. The node features can be noisy and have variance. And there may be some abnormal features in the node features. So just by using the low features can make along predictions. But taking the average And thanks to the homomorphy, we can surely say that the most of the surrounding nodes have the same level. So we can reduce the noise by taking the average, and taking the average, the node features are concentrated on to the center or the mean vector of the true level, so that we can make the embeddings in a clustered way, like the previous visualization shows, right? So we can say that GNNs much benefit from homophilous graphs. And this is the key of the success of GNNs. And yeah, it is worth mentioning that recently many GNNs for heterophilous graphs, which means graphs that do not show homophilous properties, have been proposed, like H2GCN and FA-GCN and so on. And indeed, these GNNs show promising performances, especially H2GCN performs better than standard GNNs, both in heterophilous and homophilous graphs. So such adaptations, such GNNs are very promising. But for the moment, basically the recommendation is that focusing on designing homophilous graphs. This is most promising approach. Yeah, you might benefit from heterophilous graphs, but it may involve some hyperparameter tuning or many complicated procedures. So it is better to focus on how we can define homophilous graphs, or how we can convert heterophilous graphs into homophilous graphs for the moment. Yeah, and once you obtain a homophilous graph, if you could succeed in defining homophilous graphs, then congratulations. GNNs will surely help you boost the performance of the model by exploiting the homomorphy property. And yeah, I mentioned very simple sum and average aggregation, but actually there have been many aggregation variants. And one of the most popular choices is attention aggregation and graph attention networks. And the idea is very simple. It gathers information from the surrounding nodes by attention mechanism. It can also be formulated in equation very simply, like this. WHUL is basically the value vector, and we takes the weighted sum of the value vectors based on the attention weights. Yeah, this is very similar to the transformers. And yeah, by doing so, we can ignore noisy edges, and we can focus on informative edges, and can improve the performance compared to simple sum aggregation or simple average. And yeah, I mentioned it is similar to transformers, but we can show that transformers is a special case of GNNs with attention aggregation. Attention layer in transformer aggregates values from all items, right? It attends to all tokens in the set. And this corresponds to attention aggregation of GNNs with edges between all pair of nodes. Or we can say that a special case of GNNs that uses only a complete graph. A complete graph means the graph with edges among all pairs of nodes. So this is a special case of GNNs, and GNNs are more flexible. It can define any kind of graph structure. So we can say the same thing like the previous slide where I said GNNs are more general than standard neural networks. We can start from the complete graph, and we can, if we have many relations, and if we found some relations are noisy or not, do not contribute to the downstream task, then we can remove such edges from the complete graph. And we can try measuring the performance of this and comparing to the performance of transformers. And if it is better, and we can see, we can safely remove such edges and can obtain better models. And by doing so, we can ensure that such models are better, or at least the same level as the transformer. And in general, GNNs can use flexible graphs and edges, and rather than complete graphs, and edges give hints where we should pay attention, especially when homomorphy exists. If we have relation that homomorphy shows, then we can, this is a strong signal that we should pay attention to that node. For example, in the citation network, we should, if we pay attention to unrelated or irrelevant nodes as well, then the aggregation may be noisy. So focusing on homophilious relations improve the performance or decrease the sample complexity, and can use cleaner signals in model processing. And also, we can also use both transformer-like attention heads and GNN-like attention heads and combine them. Transformer-like attention heads attend to all the tokens or all nodes, so it's with less inductive biases, but it can be, it can be high sample complexity, but if we have plenty of data, then it can be more flexible and can aggregate informative features from the faraway nodes. And also GNNs like attention heads attend to all the, only to the nodes which have the same edges, but so it has strong inductive biases, so it can draw more clear information from the surrounding nodes. And by combining these two types of attention heads, we can complement the weakness of each other. Okay, so far we have seen how we can solve node level problems with GNNs, and let's see how we can solve graph and edge level tasks using GNNs. And as we saw before, GNNs generate the node embeddings for each node, ZV, like this. So if the graph had 7 nodes, then GNNs produce 7 node embeddings. And how we can use these embeddings to solve graph level problems. The solution is very simple, and just use a layered function to summarize these node embeddings into one graph level embeddings. The easiest choice is mean pooling, where we take averages of all the nodes like this. And we can also use max pooling as well. And also we can use more fancy choice like attention pooling, where we regard these node embeddings as tokens, and we append special class token to it, and we apply transformer to this sequence of tokens and compute the node, compute the embeddings of these tokens, and we use final embeddings of the class token as embedding for the entire graph. And ZG already contain much information about the graph and all the nodes. We can use it to solve the graph-related problems by feeding this into some machine learning models for big data, and can solve graph problems. And edge level problems can also be solved in a similar way by using just a pair of node embeddings. For example, in the link prediction task, we can solve this by defining the probability of the existing edge by the sigmoid of Z2 in a product of the Z2 and Z4, or like this. And we can define the probability, and we can define the loss function just like the binary classification. You can use log loss or whatever loss you want in binary classification, and train the model in endogenous manner using backpropagation. And we can train the link prediction model. Okay, so far we mentioned abstract procedure, how we can use GNNs, and in practice, many GNN frameworks are available. The popular choices are PyTorch Geometric and Deep Graph Library, DGL. Both are very popular, and yeah, please refer to the tutorials and the documents of these frameworks, and please choose whichever you want. And also you can find graph datasets in Open Graph Benchmark. And if you want to try graph neural networks, you can find good benchmarks in it. And also the classic data benchmarks and data sets like Color, PubMed, CiteSeer are available in these general frameworks like PyTorch, Geometric, and DGL. And these frameworks, PyTorch, Geometric, and DGL are very intuitive and easy to use. And if you're familiar with deep neural networks, then you will surely use this seamlessly. And you can also integrate GNNs into other deep neural networks in a seamless way. And yeah, this is a very simple code to define a graph convolution network. You can use GCN comb module of PyTorch Geometric to define graph neural networks. And yeah, this is in the very same way as we define standard neural networks. You can stack these layers, and if you define the forward function, then we can define the graph neural networks. And you can define the forward function just like the standard neural networks. And we can use activation functions like later from PyTorch in the same way as the standard neural networks. And the only difference is we need to input the edge index information to the convolution. Yeah, this is the only difference from the standard neural networks. And you can use other components from PyTorch, not PyTorch Geometric, but the official PyTorch can be used and combined with graph neural networks. And you can train graph neural networks in an N2 manner using the optimizer defined in PyTorch like Adam and SGD and so on to train graph neural networks in the standard way. And I provided small example where we classify the Color dataset using graph convolutional network in this crop notebook. So please see it and play with it after this lecture. Okay, so so far we saw how we use graph neural networks, and after this section, we will see the real-world problems and applications where what kind of problems GNNs can handle or solve. And the first example is social recommendation. This is basically the same standard recommendation where we are given users' buying history and we want to recommend items to users. And the difference is that we are given friendship relations of users in addition to users' buying history. So the given graph is described like this. We are given a graph with edges describing watch relations and friend relations. And then we define this problem as a link prediction problem. We want to predict links between users and items. And for the moment, suppose we do not know the friend relations, and suppose the user we want to make prediction has never seen a movie before. And in that case, standard collaborating filtering approaches cannot make effective recommendations because we do not know any preferences of her preferences on movies. We do not know anything about. So it is basically impossible, and it is called a cold start problem in the recommender system literature. But if you know the friend relationships, then we can use these data to make effective recommendations. Suppose her friends like movies Whiplash, then we can recommend Whiplash to her because her friends like this movie. And even if she has never seen movies before, we can use this auxiliary data of friendship to make effective recommendation. And this is very schematic, abstract notion of how we can use friendship relations. But actually, GNNs can do this kind of inference using friend relations in very elegant way. And because that GNNs first initialize node states by the low node features, which contain only the information about the node itself. And let's learn graph neural networks on this graph. And let's use very simple sum aggregation in this case. And In this case, we can compute the embedding of her as the sum of her feature vector and plus the feature vector, the sum of the feature vector of the her friends, x4 plus x1 plus x2. And the embeddings of the whiplash is x6 plus x1 plus x2, right? And the important observation is that the information from the friends, x1 and x2, are common in both these nodes. And because that we solve the link prediction by the inner product of the two embeddings, and it means that H6, the inner product of H6 and H4 is high due to these components. These vectors have same components, so the inner products are high. So it means that this movie is recommended to her. So this example shows that even simple sum aggregation can provide or effective recommendations based on friend relationship. And GNNs in general have more sophisticated mechanism like feature transformation and attention to surrounding nodes and so on. And it can, for example, select beneficial information and discard irrelevant friends or so on, and to improve their performance more. Yeah, the important thing is that even simple aggregation, some aggregation can utilize this kind of friend relations. And we can also think of larger examples with knowledge graphs. We can attach a rich knowledge graph to this graph and can use many relations to produce more effective recommendations. For example, we can recommend this movie because this movie was selected by the same director as the movie he had watched before, using the director edge defined in the knowledge graph. This is an example of the first order inference on the graph, and one layer GNN can infer this kind of inference. And yeah, of course, if you use more layers of GNNs, then we can infer in a multi-hop way. Like, for example, if we find that he likes movies taken in the US and in which actors in Canada starred, then we can recommend similar movies to him. And yeah, we can also think of many other relations and improve the robustness and efficacy of recommendations. And yeah, another important point is that GNNs learn these patterns automatically from the data. So even if the knowledge graphs are messy and noisy, by using the training procedure, we can train the GNNs to find important and effective relations automatically. And we need to design these relations manually and can automatically enjoy the performance improvement from knowledge graph. So this is a summary of this chapter. Graph is general and flexible again. And we can incorporate all information and many information defined by knowledge graphs and friend relationship and so on to improve the performance of recommendations and other tasks. This idea can be used for many other tasks, not only recommender systems, but also we can use this idea to the text processing and question answering and image analysis and so on. And GNNs learn useful patterns from the rich information defined in knowledge graph and other auxiliary data. And graphs or GNNs are suitable for this kind of inference because they are very flexible and we can attach many kinds of complex data to the graph and let GNNs process such complex data in a unified way. So yeah, we have two patterns. When the data are sparse, like the cold start problem in the previous example, this is a very challenging problem. For example, if the target user has never seen any movie, then it is difficult or impossible to make effective recommendations. But this problem can be alleviated by using auxiliary information like friendship relations, as we saw before. And also when data are leaked, we can attach many kinds of data. We have all information we have, like the knowledge graph and other kind of graph in the target graph, and can let GNNs learn patterns from the nuanced signals written in such knowledge graph and other kind of graph data, and boost the performance by extracting information from it. So we can say that GNNs are helpful in both regime of sparse and rich regimes. Yeah, this is the basic how GNNs can help boost performance of downstream tasks. And from this point, I will show some real-world examples proposed recently. The first example is the factual question answering with large language models. You may know that large language models are suffer from hallucination and can answer the question not based on the facts, and can generate ridiculous answers to the question, even if it looks like very plausible. So we can alleviate this problem by using knowledge graph and graph networks. This paper, graph network prompting with large language models, appeared in AAA this year, tackled this problem. The problem setting is the same, almost the same as standard question answering. We are given questions, question and choices, and we want to answer the question. The difference is that we have knowledge graph, and we want to use this knowledge graph to answer the questions more accurately, or based on the facts written in knowledge graph. And the method is a little bit complicated, but the idea is simple. We first retrieve a relevant part from the knowledge graph. This is because the knowledge graph is very large, so it is not efficient to process the entire knowledge graph. So we first extract relevant part from the knowledge graph to the question and the options at hand. And we compute embeddings by GNNs, the embeddings of the knowledge graph. And these embeddings contain much information and about the questions and the facts and knowledge. And we feed these embeddings to the knowledge to the large language models. And LLMs can extract many information from the embeddings and can produce accurate answers to the question. And more specifically, this method uses a little bit complicated procedure, and more specifically, this method extracts knowledge graph for each option or each choice. So for example, if we have 3 choices, this method extracts 3 knowledge graphs, and it computes the embeddings for each knowledge graph. So we have 3 graph embeddings. And we concatenate these embeddings, or we prepend these embeddings as prompt to the text, which describes questions and options. And we feed these sequences of tokens to the large language models and let LLM answer the question. And we train the graph embedding so that LLMs can answer the question correctly. And this is the result, which clearly shows that the benefit of the knowledge graph and the graph prompting. And it even shows more than the boost of more than 10% accuracy in some settings. So yeah, this shows how benefit knowledge graphs and GNNs are in question answering setting. And the next example is from the different domains, namely the physics simulators. This paper, learning mesh-based simulation with graph networks, tries to build a physics simulator based on graph networks. Input is the state of the material, like cross, and we want to estimate how the material or the cross changes or moves. And this method represents the material as a mesh graph, like the mesh on the cross. And the idea is that each point interacts with its neighbors. It may, for example, the point in the cross may be may affect the surrounding nodes and so on. So this is like message passing mechanism of GNNs. And also we can observe that near points will move in similar directions. For example, in a specific point in a crows moved left, then we can expect that the surrounding points also move left. So this is a homophily. There are labels or the barriers of nodes, surrounding nodes are basically the same or correlated. So we can, from these observations, we can expect that GNNs are good candidates to solve this problem. And the bottom picture shows how this problem can be solved by GNNs. And we're first define the graph based on the current state. And we feed this graph to the graph networks, and GNNs predict the movement and the next state of each point. This is basically the node regression problem. And by doing so, we can predict the state of the next time step. And we iterate this process by feeding back the result to the graph networks again and predict the next time step and next time step and so on, like autoregressive way. And we can predict the future states of the material. And this is the example results of the proposed method. And we can see that the simulations are very natural and high quality. And looks like ground truth. And this idea can be used for other kind of tasks like simulating how the materials bend or the aerodynamics and thermodynamics and how flags flaps and so on. And the advantage of this approach is that be aware that this kind of problems can be solved by using the solver for differential equations. But the advantage of the graph networks is that several fold. The first, the GNNs can strike a better trade-off between the speed and accuracy, because GNNs do not need to fit, do not need to be general. It can fit to the dynamics or the distribution at hand. So it do not need to be general. So it can focus on the task at hand, and we can use the smaller GNNs to speed up the computation, keeping the performance of the accuracy of prediction. And also the strength of this approach is that we can apply this approach to the dynamics where we do not know the exact formula, but we only have the observational data. And also it may be beneficial that GNNs are differentiable, so we can incorporate this model or the simulator, resulting simulator to the other neural networks as a component. Okay, so yeah, this is an example in the physics domain. And also we can use GNNs to classify images. This paper, Vision GNN, an image's worst graph of nodes, tackles this problem. And the task is standard image classification using ImageNet. And the proposed method is like vision transformer, but graphs guides the attention using graph neural networks. The input graph is where nodes are part of the images, and we use a k-nearest neighbor relation as edge. The k-nearest neighbor with respect to path embeddings as edge. So we can think of this as the first version of vision transformer. And this is a result. And we can see that the proposed measure is better than the standard vision transformer. And this result can be understood by the explanation I used in the generality of neural network, graph neural networks compared to transformers. Because that graph neural networks is more general and the transformer is a special case of a graph networks. So if let k tend to infinity, then all the patches are connected. So this method is reduced to the standard transformers, right? So this encompasses the special case. The vision transformer is a special case. And we can choose the k and tune the sparsity of this attention, and there should be some sweet point that can achieve higher performance. And so we can ensure that by setting k as infinity, we can at least achieve the same performance as vision transformer, and we can choose this and tune this to achieve higher performance. So this is also an example of the generality, the effectiveness of generality of graph networks over transformers. And the final example is generative models for graphs and molecule data. And you may know that thanks to image models are popular these days, thanks to that strength of diffusion models. And you may have tried some models like stable diffusion and Midjourney and so on. And such models can generate high quality images from tags like this. And these models are used in many domains and business and used for hobby usage and so on. And these models are great, but it would be great and useful if we could do this with molecules. For example, if we specify the properties of molecules like organic, water soluble, lightweight, inexpensive, and non-toxic, and so on, and if we model generates the graph or the molecules that meet this property, then it will be great and can be used for drug discovery and so on. And it may be more than great. It can save lives and people and so on. So it should be a promising and very attractive task. And actually, many generative models can be used for graph data just by replacing the components with GNNs. For example, if you replace the unit for diffusion models with GNNs, then you can generate graphs just like images. And you can also use VAE and GANs for graph generative models. And there are many models that adapt these approaches. And in this lecture, I introduced the diffusion models because they are popular and standard choices for image generation these days. And the basics of diffusion models is that they take noisy data and estimate the noise. And starting from complete noise, they iteratively refine the data by estimating and subtracting noise. And this is, example. Starting from complete noise, it estimates the noise and subtract the noise and repeat this process and define the image and generate the high quality image starting from the complete noise. And the same idea can be applied to graphs just by using graph networks as a component. By this GNN takes a noisy graph and estimate which edges and features are noisy and subtract such components from the noisy graph and repeat this process. And this animation shows an example. Starting from very noisy graph, we can subtract edges like this and refine the quality, and we can obtain high quality edge, a high quality graph like this. Very simple idea. And actually, there have been many diffusion models for graphs have been proposed in the literature. This paper, score-based generative modeling of graphs bears a system of stochastic differential equations or examples. It models the denoising of the graph structure and the node features and apply the same idea to the diffusion model and obtain the generative model for the graph data with node feature vectors like molecule graphs. And you will see many examples if you Google graph diffusion models in Google Scholar or not. And this is a very hot topic, and they're developing area in graph generative modeling. But unfortunately, graph generative models have not been so successful than image and text generative models. The image and text generative models have been used in the real world and revolutionized many processes in the real world already. But graph generative models are partly succeeded, but not so successful than compared to the image and text generative models. This is partly because graph data are scarce. The success of image and text generated models depend on the rich data and huge unlabeled data posted and available on the internet. But unfortunately, people do not post molecules on the internet. People do not post molecular data to the Facebook or not. So the amount of data available for graph generated models are much less than the data for image and text. So it prohibits the growth of graph generated models. And this is serious and important problems, and many researchers are aware of this problem, and they much effort have been devoted to overcome this issue. And there are some, this is an open problem and very hot topic, how we can overcome this problem. But there are, I introduced two promising directions. The first is, yeah, it may be naive, but use large language models and model the scientific papers and textbooks on molecules and drugs, and let models acquire common sense in chemistry and pharmacy. And then we can reduce the sample complexity and can, maybe it will let generative models make high quality data using less levels. And yeah, there are plenty of approaches and methods proposed in this direction. And yeah, one of them is, what can large language models do in chemistry paper investigated the power of GPT-4 in molecular design related tasks. Yeah, and some tasks GPT-4 succeeded in overcoming this kind of problem, but the success is still limited in some tasks. And yeah, it is partly because the law of chemistry and molecular data are very complex, and it is very difficult to let LLMs to infer in a rigorous way. So yeah, the success is limited currently, but I think this is one of the promising direction, because we can utilize rich plenty of data written in the text about chemistry and molecules. And yeah, the fact that we do not have any much drug data in the graph form, so it may be necessary to use such auxiliary data in the text form. And the next direction is to use a feedback from simulators. And the characteristic of graph and molecular design is that we can use simulators to simulate the effect of molecules. This is in contrast to the text and image domains. We need to hire humans to judge the quality of text and images. And it is difficult to let the machines to automatically quantify the aesthetics of text or images and so on, where we need to build many level data to train such models. But by using off-the-shelf simulators, we can predict the performance or what will happen when we use molecules. So yeah, this is a characteristic of molecular design, and we can adapt the approach like reinforcement learning from human feedback, but from similar feedback. And compared to hiring humans, using similar is cheaper, so it may boost the performance of molecular generative models better than just using the level data. And actually, many reinforcement learning based graph generation models have been proposed in the literature. And yeah, it is promising in some directions, in some domains. But yeah, as I said before, the success is still limited. And I think, yeah, we need, yeah, these papers and researchers do not employ larger computational resources like the one used for training GPT-3 or 4. So I think the scaling is very important to be success in this direction, because reinforcement learning is very computational demanding and require many samples to be successful. So yeah, I think the more efforts need to be devoted to make this direction successful, but I think this direction is more promising approaches to overcome the problems of lack of data in the molecular domains. Okay, so that's almost all of this lecture, and let's proceed to the conclusion. And the main message in this lecture is that GNNs and graphs are very general and flexible, and it can formulate and solve many kinds of tasks and data, including recommender systems, image classification, physics simulation, drug discovery, and so on, ranging from many domains like computer vision and social science and life science and so on. And another important conclusion is that we can build graphs with various information using like knowledge graph and other kind of auxiliary data, and help boost the performance of the models at hand. Compared to just using the sample separately, we can use such auxiliary information to improve the performance. And this idea can be used for any tasks, literally any tasks, thanks to the flexibility of graphs and GNNs. We can apply this idea to the image classification and text analysis and so on. So whatever your field of interest is, you can apply this idea to your field. And yeah, I hope and I believe that this lecture and GNNs will help you improve the performance and the boost the performance of your model and helps solve the problem you're facing. Okay, that's all. Thank you for listening.